1967, Cambridge University. A young graduate student named Jocelyn Bell is firmly convinced she doesn't belong here. Working under her supervisor, Anthony Hewish, Bell is tasked with analyzing miles of paper printouts from the university's new radio telescope. She meticulously reviews the charts by hand, expecting to be thrown out of the prestigious program at any moment. Late one night, poring over the data, she spots something strange. She describes it in her notes simply as a bit of scruff on the printout. Space is a noisy place, overflowing with chaotic, random radiation. But this signal isn't random. It pulses with a flawless metronomic rhythm, repeating exactly every 1.337 seconds. A natural object shouldn't be able to keep time like that. The precision was so highly engineered that for a brief window, the research team legitimately considered they might be listening to an alien beacon. They even dubbed the signal LGM-1 for Little Green Men. Hewish is highly skeptical and demands they verify the find. During a tense follow-up observation, the team waits at the telescope, but the signal is nowhere to be found. A nervous Bell realizes she made a 5-minute miscalculation in her tracking. When they adjust the timing, the pulse is right there, ticking away. Confirming the repeating signal ruled out Earth-based interference, and eventually ruled out an alien origin. Astrophysics had a strange new problem to solve. They had to find a natural stellar object capable of perfect clock-like precision. The source of the signal was the explosive death of a massive star, a supernova. When a giant star detonates, it leaves behind a core that collapses in on itself. The intense gravitational pressure forces protons and electrons to merge, creating a sphere made almost entirely of neutrons. This is a neutron star, an ultra-dense remnant roughly the size of a city, but containing the mass of a sun. This sphere spins incredibly fast, generating a massive magnetic field that blasts intense radiation beams from its poles. Crucially, these poles don't align with the star's rotational axis, so as it spins, the star whips those beams across the cosmos in a massive sweeping circle. If Earth happens to sit in the path of that sweeping beam, our telescopes detect a sharp burst of radio waves every time it flashes past. The LGM-1 mystery was solved. Humanity had discovered the pulsar. The discovery was monumental, and in 1974, it earned the Nobel Prize in Physics. However, the award was given to Anthony Hewish. Jocelyn Bell Burnell, the student who actually spotted the anomaly in the data, was excluded from the prize entirely. Her reaction to the snub was remarkably graceful. She maintained that awarding a graduate student would demean the prestige of the Nobel Committee. Regardless of the hardware, her meticulous observation secured her legacy as a pioneer for women in science, while providing astronomers with the first precise clocks found in deep space. Pulsars are incredibly stable. Because they carry so much momentum, their rotation rates rarely slip. Over decades, their pulses remain as accurate as the most advanced atomic clocks on Earth. This universal precision makes them perfect for deep space navigation. When NASA launched the Pioneer probes, they included a plaque featuring a map of 14 specific pulsars. These act as cosmic lighthouses, showing anyone who finds the probe exactly where our solar system is located. Fast forward to the modern era, and astrophysicists realized this clock-like reliability could be utilized for something far more ambitious than creating a map. If you monitor a large enough network of these stars simultaneously, you can turn our slice of the Milky Way into a single massive instrument. This is a pulsar timing array. By tracking the exact arrival times of radio pulses from 68 specific pulsars, scientists built a galaxy-sized detector. The target for this massive array was supermassive black holes, specifically pairs of these billion solar mass giants orbiting each other at the centers of merging galaxies. The orbital dance of these immense objects creates long wavelength gravitational waves that rhythmically stretch and compress the fabric of spacetime. As these ripples wash over our galaxy, they alter the distance to the pulsars. Measuring these nanosecond delays revealed the universe's low-frequency background hum. Hearing this hum required an immense global effort. Researchers dedicated thousands of hours a year on the world's largest radio telescopes, collecting data for over 15 years to finally spot the pattern. The bit of scruff spotted in 1967 revealed a new class of stellar remnants. Decades later, they provided the first evidence of a gravitational wave background, allowing us to observe collisions of the largest black holes in the universe.